All right.
So the second talk of this morning will be given by Scott Aaronson, and he's going to tell us about gentle measurement and differential types.
Okay, thanks. So, yeah, so I had hoped that at this workshop, I would have been able to give you a talk about, an exponential quantum speed up for some well-defined machine learning problem, that matters in real life with classical inputs and classical outputs. Problem is, I don't have such an example. I thought that there would be one. I thought that this Karanidas-Prakash algorithm for recommendation systems was going to provide an example of an exponential quantum speedup in query complexity, and that would be provable by giving a classical lower bound for the problem. So I gave that problem to an undergrad named Ewin Tang, but the result turned out to be the opposite. There is a fast classical algorithm, but that's a talk for Ewin to give sometime. So so I'm going to talk about something else, but I think still within the scope of this workshop. I'm going to talk about the use of ideas from classical machine learning, and in particular from differential privacy, which is an offshoot of machine learning, where you actually care about protecting the user's privacy in your machine learning algorithm, to problems of quantum measurement. Okay, so this is kind of to me a surprising connection that we made this year. So this is joint work with Guy Rothblum at Weizmann Institute, who's a classical differential privacy expert. And like most of my work, it is in preparation, in the process of being written up. No, but this one should really, really be done soon. Okay, so so the starting point here. So what is gentle measurement? Well, measurement in quantum mechanics, as we all know, is an inherently destructive process, right? You take a state, you ask it what it is in a basis where it's far from any basis vector. Well, you force it to drastically, violently change. Okay, but not all measurements are destructive on all states. Okay, so there's some information disturbance trade-off, which can be formalized with various results, like the so-called gentle measurement lemma, which, in words, basically says that if I measure a state, in a basis where that state is close to one of the basis vectors, right? Or more generally, where, if given knowledge of the state, I could almost perfectly predict the outcome of the measurement, well, then that measurement can be implemented in a way that only damages the state by very little. Okay? So, and I have to include the phrase "can be implemented" because there may be so even like once I specify a measurement in the sense of giving the POVM elements, there could be many different ways of implementing it that would give rise to different post-measurement states, right? As a silly example, I could do the measurement and then just apply some unitary afterward, right? Okay, well then. In that case, the measurement was not gentle, right? But the point is that any measurement, whose outcome, given knowledge of the state, could have been very well predicted, can be implemented in a way that is very non-destructive. Okay, and in that case, you can actually keep applying those sorts of measurements over and over again without actually damaging your state. Okay, and this is not trivial. Because it's not that it's not merely for cases where you already knew the measurement outcome, right? It's in any case where given knowledge of the state, you could have known you would have known the outcome. But but in general, someone hands you a state, you don't know what that state is. So you can actually learn something by measuring it, and yet without damaging it. Okay, so so more formally, let's call so given some measurement m, like a POVM, whatever. Let's call it alpha gentle on a set of states S. If for every state, for every mixed state row that's in that set, and for every possible outcome y of applying the measurement, let's say the measurement m can be implemented in such a way that the post-measurement state, if the outcome is y, has trace distance at most alpha from the original state rho. Okay, so this is a strong requirement, right? I'm requiring this for every possible outcome of the measurement. Okay, but if this is true, then we will call that measurement alpha gentle. Okay, so so now what are examples of sets of states S that we could be interested in here? Well, maybe the most obvious choice would be just the set of all states, right? The set of all mixed states on d dimensions. Okay, but not surprisingly, one can prove a proposition that says that if your measurement is alpha gentle for some small alpha on the set of all states, then it is a nearly trivial measurement, right? It just barely depends on the state at all, right? If you want your measurement to learn anything, then on some states it's going to be damaging, right? But okay, so a more interesting example is, let's look at the set of product states. Okay, so consider measurements that are gentle on all product states. Okay, and here there are actually very non-trivial examples of measurements that are gentle, and actually this has been well known in in parts of physics for a long time under different names. This is related phenomena have been well known in this field of weak measurement, for example. Okay, so let me give you an example. Let's say that we just had a collection of n qubits, in a product state, right? So I'll even just assume that they're identical, right? So we have a state like this, okay, and let's say that I want to do a measurement that tells me the total Hamming weight. Okay, well that in and of itself is going to be a very destructive measurement in general. Okay, why? Because if I look at the superposition over the possible Hamming weights, the string, right, it is a Gaussian, right? It is what a physicist might call a Gaussian wave packet. Okay, like centered at I guess beta squared times n. Right, and with some width, of order square root of n, right? And so if I just measured the total Hamming weight of my string in the superposition, then what I'm doing is I am forcing this wave, I am localizing this wave packet. I'm forcing it down to a single Hamming weight, and that's a very destructive thing to do. Okay, but let me show you a much gentler thing to do. Okay, something that is gentle on all the product states. Well, what if I have a measurement that just tells me the Hamming weight plus some deliberately added noise? Okay, so I say I'm going to add some noise, and actually a good choice here turns out to be what's called Laplace noise. And this is noise, that has this kind of distribution. So like the noise, I'll add an amount of noise k, where k is some integer with probability that scales like e to the minus epsilon times the absolute value of k. Right? So it's just like Gaussian, except instead of squaring, I just take absolute value. Okay, and the mean absolute value, call it sigma, should be large compared to square root of n. Okay, then so now, like, instead of just measuring the Hamming weight, say of my string x, I'm going to be measuring this x plus k. Okay, and I'll implement a measurement that only tells me this. Okay, so for example, if I take my state, and then I also take a superposition over, the different possible values of the noise, like this, then I'm saying that what I would do is now compute the Hamming weight plus the noise in some third register. And then using this register together with this one, I would uncompute this register, right? Just reset it to 0. And then measure only this, okay? Then the claim is that on every product state, this state will be damaged only by a little bit. In particular, it will only be damaged by an amount that's like a square root of n divided by sigma in trace distance. Okay, so it will be this gentle. So if sigma is like between square root of n and n, then the upshot is I will learn something about the Hamming weight. Actually, I'll learn a lot about it. I'll get a rough sense of where it is, and yet without damaging my states by much. Okay? Yeah?
Is that true for all possible ones, or are there some like super unlikely outliers where you might damage it?
Excellent question. This is actually true for all possible outcomes of the measurement. Okay? And the reason is that no matter where, if I had added Gaussian noise, that would not have been true. But with Laplace noise, it is true, okay? And the reason is that with Laplace noise, like no matter how far out I go in the tail, like I have some like multiplicative guarantee over here, okay? So I have some like multiplicative closeness there, okay? You can confirm what I just said by calculation, by just a laborious calculation. But actually, the nicest proof that this thing really is square root of n over sigma gentle will just be to deduce it as basically an immediate corollary of the main result that I'll tell you about today. Okay, just as a little byproduct. Okay, so but intuitively, what adding the noise is doing is it's sort of smearing out, over the different components in this wave packet, right? Like the problem with measuring the Hamming weight is that it separated the different, components within the wave packet, right? It separated this part from this part and so on. But when we add this noise term, then, no matter where we are, like, let's say within, let's just think about the fat part of the Gaussian, right? No matter where we are there, we're getting basically the same distribution over outcomes, right? And so we're not sort of learning where we were within the Gaussian too well, and so so the Gaussian is still intact. Okay, so so that's this is a known technique. Or things like this are, as I said, known techniques in experimental physics even. And so what happened was like a year ago, I gave a talk at Weizmann Institute. Where I talked about some new protocol, some then new protocol that I had, which was called shadow tomography, and I'm going to tell you more about that later in the talk. Okay, but a central ingredient in shadow tomography, as in a whole bunch of previous results that I've proven in my life, was this gentle measurement. Okay, it was implementing measurements gently, and so I discussed this example and. Guy Rothblum was in the audience, and then afterward, he asked to meet me for lunch, and he said, listen, this thing you're talking about, it sounds just like differential privacy, which is the thing that he works on, okay? And I said, come on, like, anyone, like whenever anyone goes to a talk, they always think that it's just like whatever they work on, and it's like, you can relate anything to anything else with sufficient creativity, right? And that this is there's probably nothing to this, okay? But just to be polite, I said, all right, I'll spend like a night thinking about it, okay? So I did I did that, and then I send an email to Guy, like holy crap, there is it looks like there actually is a very strong connection here, but. Okay, so now I have to back up and say, what is differential privacy? Okay, so this is a new area of CS, new since like 2006 or so. So newer than quantum computing actually, and it is all about how can you have a database with some very sensitive data in it, like people's medical records, their financial records, whatever, and you know, and then like allow some, let's say, researchers to data mine this database, you know, and make queries to it, so that they'll learn you know, they'll learn something useful, but there will also be a mathematical guarantee that you're not going to be revealing too much about any individual user, you know, or any one entry, or any small number of entries in this database. Okay, you know, I mean, there's like a philosophical question. What do you even mean by that, right? Let me tell you the definition that people converged on in this field. Okay. So let's say, you know, we have an algorithm A, you know, a probabilistic algorithm, whatever. When we're going to say that it is epsilon dp, epsilon differentially private, if for every possible database X, okay, and I'll think of a database that's just like a list of n records, you know, x1 up to xn. And for all neighbors x prime of x, what do I mean by a neighbor? I mean a database that you could get by just changing x in any one record. Okay, so you know, it differs from x on one record, and for all possible outcomes y, you know, for all possible outputs y of this algorithm, switch pens. The probability that A outputs Y on input X is at most e to the epsilon times the probability that A outputs Y on the database X prime. Okay, so so we ask for like a multiplicative closeness in the probabilities for every possible output of the algorithm on every possible pair of neighboring databases. Okay, so one person changing their data or dropping out of the database can change the probability of any output of our algorithm by at most an e to the epsilon factor. You know, and this basically just means 1 plus epsilon, except that it composes better. Okay, you know, this sounds like a very strong criterion, right? But you know, why do we want something so strong, right? I mean, like your first guess may have been just if one user changes their data, then that should have only a small effect on the variation distance, something like that. Okay, but if that's all you wanted, well, then you would have to say that the following algorithm was very private. Just pick one user at random and publish all their data, right? You know, since that user probably won't be you, you know, you have a good variation distance guarantee, right? Okay, so we don't want to say that, right? So the multiplicative criterion, you know, avoids that problem and has, you know, has many other nice properties, okay? So, yeah, right. That's right. Yeah. So, you know, and by the way, like you know, I was sort of, you know, aware of this, you know, this subject for more than a decade, and I never paid the slightest attention to it because I said, all right, this is just, you know, some theorists like trying to like get on some bandwagon of, oh, people care about privacy, so we're going to make something up about privacy. And, you know, like, what do I care about privacy? I just publish everything on my blog, right? But it turned out that I was completely wrong. And this is actually a really, really deep notion that's connected to many, many other things. Even before the connection that we made, it turns out that, you know, that differential privacy, you know, some beautiful work 4 years ago by Cynthia Dwork et al. It was connected to what's called adaptive data analysis, right? So you may have heard of like this, you know, replication crisis in like social science research, where, you know, people like, you know, it turns out that like a huge number of studies, you know, where we're really just, you know, the results were just artifacts of p-hacking and so forth, and, you know, and they don't replicate, right? And, you know, and part of the problem here is that, you know, people sort of just took the same data sets and they just used them over and over, right? Just data mined them over and over. And, you know, but if you do that, then you know, the very question that you're asking, you know, the next time, you know, you look at the data may depend on the answers to the previous queries that you made to the data. And therefore, this data is not fresh to you, right? The data is like, as it were, contaminated by the fact that you already used it, right? And that you already conditioned on some result of querying it. And so people realized that problem. And they said, you know, well, so is there like a way that we can query our data more safely? And so 4 years ago, they made this connection that that actually, you know, you can it's fine to keep reusing the same data set over and over, even exponentially many times, as long as you use an algorithm that is differentially private. Okay, so, you know, and if you like that's sort of like, that was sort of like the classical predecessor of the connection that we're going to be making in this talk, right? Where like instead of quantum gentleness, they were talking about classical Bayesian gentleness, right? But all right, so this turns out to be, you know, a pretty fundamental notion, you know, for more than just privacy, right? You know, it is also being used, apparently both Apple and Google are actually now using differentially private algorithms, you know, when they do their data mining. But I was reading news articles that says that Apple set this parameter epsilon to be so large that it doesn't give you actual privacy in practice. But you know, apparently Google is doing somewhat better. But you know, that's just what I read. I don't actually know the details of how it's being used. But let's see an example of a differentially private algorithm. Okay, so again, you know, let's say that we have like a database that just consists of n bits. You know, like for each of our, you know, n patients, do they have colon cancer or not? Something like that. Okay, let's say that's X, right? And now, you know, we want to do a query. Well, a very simple query would be, you know, how many people have colon cancer in our data set, right? Now, this is not differentially private, right? So, for example, like, you know, if we see that like one new user has just joined our database, and at the same time, you know, Bob, and at the same time, the number with colon cancer has just gone up by 1. All right, we've learned something about Bob, right? So this is not safe. Okay, so what do people do in differential privacy? Well, they deliberately add some noise to the query before they return it. I mean, that is one of the basic techniques. So, for example, we could say, instead of just returning the Hamming weight of the string, return the Hamming weight plus some Laplace noise term, call it K, you know, that looks like this. Okay? And, you know, it's easy to see that this is going to be differentially private. Why? Because, you know, if I look at two two databases, two strings, say, that differ in one place, right? Then the difference in their Hamming weights is 1, right? The Hamming weights differ by 1. And so now I fix, so I look at probability that, I look at the ratio of the probabilities like this, right? And I look at, and so this is basically just e to the minus epsilon times, absolute value of, I guess, the Hamming weight minus y, right? Right, like that. And this is like e to the minus epsilon, the Hamming weight of x prime minus y, right? But, I said that these differ by at most 1, and so this is at most e to the epsilon, okay? And that's why this is differentially private. All right, so as I said, Guy, noticed the seeming coincidence between the different types of techniques, and he said, I wonder if there is a connection here. So, okay, so we can easily come up with a quantum generalization of this definition of differential privacy, right? We'll just say a measurement M is epsilon differentially private on a set of states S if for all states rho in S and all neighbors rho prime, by which I'll mean, states that you can get from rho by, say, applying a super operator to one register only, right? I'll think of this as a state on n registers, and a neighbor is just a state that I can get by acting on only one register, and for all possible outcomes y of the POVM, the probability that my measurement on rho outputs y is at most e to the epsilon times the probability that the measurement on rho prime outputs y. Okay? Good. So now our central result is a very strong connection between this definition, measurements being epsilon differentially private, and the measurements being alpha gentle. Okay? And then, we can moreover use that connection to do some things that hadn't been previously known. So, I'm not deeply concerned with, preserving the privacy rights of qubits, but, this definition is, a little bit interesting, even just in and of itself, because what it would give you is a sort of natural robustness of your measurement to like a failure in any one of the states or any small number of states, and it's a robustness that doesn't depend on doing any error correction. Right, if you have this, okay, and so again, the way, so just a sec, once again, one can show that the only, if epsilon is very small, then the only measurements that are epsilon differentially private on all states whatsoever are measurements that are close to trivial, right? That do nothing. If epsilon is like, let's say, less than 1 over n, something, right? Well then, I could just change each register one by one, and my probability is still not changing by much, and so then now I've got a completely different state, right? So so you could say like at one extreme of parameters, differential privacy and gentleness clearly are the same thing because they're just both equivalent to triviality, right? But what we're going to do is we're going to prove a much more interesting connection than that between differential privacy and gentleness, one that encompasses many non-trivial measurements. And to do that, we will typically have to make the assumption that our set of states S is a set of product states, for example. Yeah, question. Yeah. Well, no. So, no. What I told you what I mean by neighbor. That you know, it's a state that you can get by acting with a superoperator on one of the n registers. Okay, this is a state of n. Okay. Yes. Right. Right. So, all right. So, like in the special case where we're talking about product states, you know, all we mean is that you have changed at most one of these states that's in the product, right? Like that. Okay? All right. So, all right, so let me tell you our main result. Okay. Mm. Okay, so the first, so there are two parts. First part is very, very simple. It says take any measurement that is alpha gentle on all product states, where alpha is sufficiently small, right? Let's say, you know, less than a quarter, okay? Then M is also O of alpha differentially private on all product states, okay? And you know, importantly, you know, it is possible to be alpha gentle on all product states without being trivial, you know, as in the example that I showed you before, with, you know, where you compute the Hamming weight plus some Laplace noise, right? So this actually, you know, encompasses some things that are interesting. Okay, now, and by the way, this part, like once you've decided to ask the question, this part is like a few lines to prove. Okay, this is a super easy proof. You know, I can do it later if people really want to see it, but it's, you know, okay. Now the second part is the part that's both, you know, a little trickier to state and also a lot trickier to prove. Okay. Mm-hmm. Okay, so suppose that M is epsilon differentially private. I'm going to say where epsilon is small compared to 1 over square root of n. Okay, on all product states, you know, of n registers, and also M can be implemented by just applying, you know, a product of POVMs. Right, so we apply a POVM separately to each of the n registers, and then you do whatever classical post-processing you want with the results. Okay, so I'm going to assume that M has that special form. Okay, admittedly, that seems like a strong assumption, but that set of M's actually encompasses all the differentially private algorithms that we actually know or care about in practice. Okay, I mean, you know, we can construct quantum differentially private algorithms that do not have that special form, but so far, you know, we only know how to do it by making up super artificial examples, right? all the things we care about, that we've known or cared about in practice, have had this form of being product measurements. Okay, yeah. Well,
product space and only product measurement.
Well, but the states are still quantum states.
Think of it as like a Heisenberg spin, essentially like instead of like.
Well, okay, but you know, there's no restriction on the local dimension of these states, right? They don't have to be qubits. They could be each one can be states in whatever dimension you want. Okay, they could be, each one itself can be a complicated quantum system. Okay. Yes. each one can have dimension 2 to the 1,000th power. That's fine. Okay, right? Okay, and you know, and I'll show you how to use this to get, you know, a quantum measurement procedure, you know, that we didn't know before. Okay. All right. So then the conclusion. But by the way, even if they were just qubits, you know, this is already like a statement that's not entirely obvious how to prove it. Okay, the conclusion is that M has some implementation, which is O of epsilon times square root of n gentle. Okay, so you know, so again, you know, or you know, if we just define a measurement to be gentle. You know, if it has a gentle implementation, then we can just say M is O of epsilon times square root of n gentle. Okay, so you'll notice, you know, we're losing a factor of square root of n here, but this can be proven to be necessary. Okay, this is actually tight. Okay, and the example that shows that it's tight is, you know, once again our favorite example of just take the Hamming weight and add some Laplace noise to it, right? So, you know, if we, so let's just, consider that measurement, right, where we have this Gaussian wave packet. We want to measure the Hamming weight plus Laplace noise. What one can show is that, let's say, you know, the noise, you know, has average magnitude sigma. Then this gives you a measurement that is 1 over sigma differentially private, right? And also it is, as I said before, it is square root n over sigma gentle. Okay? So in particular, like if sigma were small compared to square root of n, right? Then this would be an example of a measurement that is has very good differential privacy, but that has no good gentleness at all, right? Like if I only added noise that was small compared to square root of n, well then I would be separating my wave packet into different components. Okay, so it shows that that there is a regime where you have differential privacy, but you don't have gentleness. Okay, but what we're saying is that there's also a very interesting regime where differential privacy does imply gentleness. Okay, and that is the regime where, let's say, epsilon is somewhere between 1 over n and 1 over square root of n. Okay, yeah?
What about counterexamples when it's not a product?
Ah, excellent, yes. So now, okay, so I don't know. So actually one of our main open problems is, we conjecture that a similar statement should hold, when M is an arbitrary differentially private measurement. Yeah.
You actually look for measurements that should preserve some kinds of differential privacy and be gentle. And things that are local measurements are probably more private.
Intuitively, you would think so. Yeah. I agree. Yeah. I agree. We couldn't figure out how to show that, and so that's a big open problem we leave. Extend our, part 2 of this theorem to arbitrary measurements. Okay. Now one thing that we do know is that it is necessary to assume if you want this statement, then it is necessary to assume that we're acting on product states. Okay. So here, and in particular, if you wanted if you wanted gentleness on all states, then all you would get is that your measurement is O of epsilon times n gentle, rather than square root of n. Okay, now what's the problem with that? That sounds like a mere quantitative issue. Well, the problem is then, in that case, you'd only get anything non-trivial if epsilon is small compared to 1 over n. But the only measurements that are epsilon differentially private, where epsilon is less than 1 over n, are nearly trivial measurements, right? So then, you only get the trivial statement, okay? And here, there's a very instructive example to show this, which is just look at a Schrodinger cat, right? Or, or a GHZ state, whatever. Or, in fact, we could just as well just look at a probabilistic mixture of the all 0 string and the all 1 string. That would work as well, okay? So this is not a product state, obviously, right? And then what is it that breaks down, that has to break down in this theorem, right? Well, take the measurement that just tells you the Hamming weight plus some Laplace noise, let's say of order n to the 0.99 or something, right? Okay, well, that's that's going to be very nicely differentially private, right? But that's clearly not gentle at all in this state, because it still quite well tells you whether you were in the all 0 state or the all 1 state, right? And therefore it collapses your state. Okay, good. So oh yeah, so compared to the the earlier work that there was about adaptive data analysis, the main you could say the main difference with this theorem is that we're talking when we talk about gentleness here, we're talking about actual physical damage that can occur to your quantum state, right? Whereas in this earlier work, they actually had some similar statements to this one. They were talking about Bayesian damage to your probability distribution, which is, something that happens in your head. And that damage could be reversed by the simple expedient of forgetting whatever you had just learned, right? So, but yet mathematically, they're kind of similar. Okay? So, all right, so I'm probably not going to have time to go through, the way that we prove statement 2 here. But just to give you a rough idea, what we do is actually we first prove a classical version of this statement. Okay, we first prove it for the special case where we just have a product classical probability distribution, and we are just looking at it. We just have a classical DP algorithm, and then. What you can do is just by using the fact that your algorithm is differentially private, you can take you want to you have some product distribution like that, and then you have the posterior distribution. Meaning the distribution after you conditioned on the outcome being y, right? And your goal is to upper bound the variation distance between these two distributions, okay? So, the right way to do that it turned out to be forget about variation distance and look at the KL divergence, okay? As Seth taught us, everything, is better when it's KL divergence. Okay, so what one can show using differential privacy is you can show that if I just slowly revealed the elements of D prime, just one at a time, like x1, x2, x3, and so forth, and I just track how much the KL divergence between D and D prime is going up, I can show that it goes up by at most epsilon squared. okay, at each, with each database entry, using the fact that my algorithm is epsilon differentially private and using, known inequalities about the KL divergence. So then the total KL divergence is at most epsilon squared times n, right? And then you can use Pinsker's inequality. Pinsker's inequality says that variation distance is at most the square root of KL divergence, right? Which in this case would be epsilon times square root of n, and that's where this is coming from. Okay, and then the next step is now we have to extend this to the case of quantum states, right? So we start with just quantum pure state, just a product pure state, and just a product of projective measurements, right? And then that can basically just be handled by just reducing it to the classical case that we already analyzed, right? And you have to look at the inner product between quantum states, but you could give an expression for that in terms of the KL divergence between the distributions, right? And you end up using this Hellinger distance, which is another distance metric between distributions, but you end up just being able to just apply your bound on the KL divergence to upper bound the Hellinger distance and therefore the trace distance between the states, right? And then, you want to generalize it further. Okay, what about mixed states? And then you say, well, by convexity, that just reduces to the case of pure states. And then you say, well, and what if it's general POVMs, instead of just projective measurements? And then you say, well, by the church of the larger Hilbert space, that reduces to the case of projective measurements. Okay, that would be a short summary of how we prove this. Okay, and as I said, it's an open problem to generalize it still further. Okay, so as I promised, just one immediate example application of this theorem would be to prove that the measurement that I showed you at the beginning of the talk actually is gentle, right? The measurement where you just take the Hamming weight and you add Laplace noise, right? Well, it's trivial to see that measurement is differentially private, and and now you just apply part 2 of this theorem and you get that it's gentle automatically without having to do any hairy calculation. Okay, but now let me conclude the talk by telling you like a more interesting implication of this theorem. Okay, an actual application that we were able to get from it. Okay. Okay, so this concerns this problem that I call shadow tomography in a recent paper, which unusually for me is actually out, published. This actually, I had a more boring name for it, but then Steve Flamia told me I should call it shadow tomography. Physicists always have better names for things. Okay, so what is this? Okay, so the task. So for reasons related to quantum money and quantum copy protected software and quantum advice and other stuff that I care about, and I won't go into, I was led to consider the following problem, which I think is, extremely natural. Once stated, I have no idea why anyone didn't study it before. Okay, but here's the problem. Given an unknown d-dimensional mixed state rho, right? And we have some number of copies of it. Let's say, and we also have a known list of 2 outcome POVM measurements, which I'll just represent each one by the POVM element corresponding to the yes answer, right? So each of these measurements, EI accepts rho with probability trace EI rho, you know, and it otherwise rejects. Okay. Our problem is going to be to estimate trace EI rho to within some additive error of epsilon for every I. Okay. So like in full quantum state tomography, I want to learn the entire density matrix rho, right? And you know, it is known. It was actually shown only recently, but it has now been proven that about d squared copies of rho are information theoretically necessary and sufficient if I want to do quantum state tomography, right, and reconstruct rho. I mean, intuitively, that's kind of what you'd expect because, you know, rho is a d by d matrix and it's got d squared degrees of freedom in it. But, you know, but that was actually quite hard to prove. Okay, in shadow tomography, all you want is the shadows cast by rho on these m known yes or no measurements. Okay, so you know a good example might be, let's say rho is an n qubit state, and then these EIs might be all of the measurements that you can, you know, all of the yes or no measurements that you could implement with quantum circuits with at most n squared gates, or something like that, right? That would be a very interesting set of two outcome measurements. Mario? Sorry. Adaptive in terms of what? I don't understand. No. So each of these, I just want to know the probability that EI would accept, you know, rho, the original state rho. Okay. Right. The method, I can do whatever I want. Okay. So the issue, you know, right. I don't understand the question. I'm gonna be given, you know, k copies of rho. Okay. Now, given those copies, I can do whatever I want to try to get this information. Yeah, the question is how k depends on everything. Let's say, yeah. So the question is how many copies k are information theoretically necessary and sufficient in order for me to learn this information. Okay, to learn all the trace EI rhos approximately. Okay, so all right, so let's explore that question. Well, at one extreme of parameters, clearly, like, you know, d squared copies of rho are sufficient because then I can just do full quantum state tomography and then, you know, I'm done, right? I can just calculate, you know, any of these things that I want. Okay, at a different extreme of parameters, roughly m copies of rho are also sufficient. Why is that? Anyone? Well, you know, I could, yeah, I could just make each measurement on separate copies of rho, right? And then I would also be done. Okay, but again, I'm interested in cases where d and m might both be exponentially large. Okay, and the question that I asked a few years ago at a Barbados workshop was, you know, is it possible that, you know, you could nevertheless do it with k that's only polynomial? Okay, or, you know, equivalently, we're asking, can this be done with k that is a number of copies k that is polylogarithmic in both d and m? Okay, so, you know, again, you know, my guess was that this was not possible. You know, a bit like Ewan Tang with the recommendation systems, I tried to prove that and I wasn't able to, and I ultimately explained my failure to prove it with the following theorem. It is possible. What? Yes, I agree. There are many special cases where it is clearly possible. You know, the question is this possible in full generality for arbitrary E1 up to EM? And so the theorem that I had in the stock paper says that indeed it can be done with k that grows like log to the fourth m times log d over epsilon to the 4 times some log terms. Okay? So, this is, this answers my original question. It's, these exponents are kind of, maybe larger than one would like. And I've wondered, what are the optimal exponents here? The only lower bound that I was able to show in the stock paper was that at any rate, you need at least this number of copies of rho, log m over epsilon squared. Okay?
What for the full tomography?
Yeah. Oh, right, for the full. Yeah. So right. So I mean, there is a case that you can construct where you need this many, right? And and like with you'll choose D in such a way that even if it was D squared, well, D would be more, D squared would be more than this, right? So one can construct a case where this many is needed. All right. Yeah. Yes. Oh. Okay. Well, because this is so first of all, this is a lower bound. This is not an upper bound. This is a lower bound, right? That's the first point. Okay. So a lower bound can be lower than an upper bound. Yeah, the upper bound. Okay, so this upper bound. So the basic answer there is that I'm not promising you to do full quantum state tomography. I am promising you to do shadow tomography. Okay, and with shadow tomography, all you get is these things. Okay, now but this is what makes it surprising, right? You would have thought that D squared was needed, even for this, but it's not. Okay, so now you may have wondered, well, if I could do shadow tomography, then isn't there some reduction that would also give me just full state tomography? Okay, well, it turns out that there is such a reduction. If I choose an informationally complete set of measurements, right, then learning trace EI rho for all of those measurements to a high enough precision would actually would let me reconstruct rho itself, right? But in order for that to work, epsilon would have to be like 1 over m. Okay, and so then you plug into this, and and everything's consistent. Okay, good. All right. So now let me tell you what this has to do with gentle measurement and differential privacy, and then I will finish. Okay, so all right. So to make a long story short, there is a well-known classical algorithm in the world of differential privacy, which is called PMW, Private Multiplicative Weights, due to Hardt and Rothblum from 2010. Somehow Guy knew about this algorithm. Right. And what this does, it's an algorithm for taking a long sequence of queries, and answering each of them one by one in an overall differentially private manner, right? And it had some very nice features, like that it processed these queries like in an online manner, just each one at a time, without needing to see the future queries, and and pretty simple, and it's based on like half of theoretical computer science nowadays. It is based on this multiplicative weights update method, which I would tell you about if I had time. I probably don't. Okay, but so what we do is, by starting with the PMW algorithm, well, we generalize it to a quantum PMW algorithm, right? That just takes a long sequence of two outcome POVMs like this, and and implement and runs each of them one after the next on a collection of states row like this, and then by a similar analysis to Hardt and Rothblum, we show that each iteration of that algorithm is differentially private, right? In our quantum sense, is differentially private, and then by using our connection, we get that each iteration of the algorithm is actually gentle as well, and so is not damaging the states by much, which means that I can then reuse them. Okay, and then this gives us a procedure for shadow tomography, one that actually happens to be considerably simpler than my original procedure, the one that was in my stock 18 paper. And so the sample complexity that we're currently able to get for with this new procedure is that we need only log squared m times log d divided by epsilon to the 6 copies of rho. This epsilon to the 6, is worse, but we're working on it. All right, we're working on it. But concentrate on the dependence on m. Right, that's better. Okay, so we've gotten closer to the information theoretic limit here of log m. But more interestingly, this procedure is also online. So my original procedure, you had to see the entire set of measurements, E1 up to EM in advance. And then you had to do some complicated thing where you sort of identify which measurements are really important by repeatedly going through the whole list and finding a really important measurement that you then condition on to improve your hypothesis about rho, right? But it required seeing all the measurements in advance. Okay, this new procedure is online. So you just have to see the EIs one at a time. And then each one, you see E1, estimate trace E1 row. You see E2, you estimate trace E2 row, and so forth. Okay? And also, this entire procedure is gentle. So you can run the entire thing, and you still have almost the same state, row tensor K that you started with. Okay, so that is an application of our connection between gentleness and differential privacy. And I hope that more applications will be found in the future now that this bridge exists between these two fields. Okay, there are many, many other open problems that you could study here. I already mentioned, proving a fully general connection between differential privacy and gentleness is an obvious problem. For this application to shadow tomography, right? The connection that we had was enough because the measurements that arise in the Hardt and Rothblum quantum PMW algorithm, do have the form that we want. They're basically all about, just taking the sum of a bunch of individual measurement outcomes and then adding Laplace noise to the result, right? And that does fit into our format, right? But we would still like a general theorem that would, handle possible differentially private quantum measurements that don't fit that format. Okay, what is the true sample complexity of shadow tomography? In particular, we still haven't resolved the question, is this log D term actually needed here at all? Right? I don't know the answer to that. Now, it turns out that by using the other direction of our connection, by taking lower bounds that are known for differential privacy and then porting them over to the setting of gentleness, what we can show is that if you want a shadow tomography procedure that is also gentle, then the sample complexity is going to require at least a square root of log D factor in the number of copies of rho. Okay, but if your shadow tomography procedure doesn't have to be gentle, then we don't know whether even that is necessary. Okay, and so that's an open problem that interests me here. And then Cynthia Dwork, who's kind of the founder of differential privacy, her main question was, well, can we go in the other direction, and can we use anything that is known in quantum to learn something new about classical differential privacy? I don't know how to do that. I had to admit to her that I could only I could only take from her field right now and not give back. All right, so let me stop there. Thanks. Yeah. Well, yeah. Well, I'm saying that we construct a scenario where this many is needed. I don't know what you mean. We construct a set of EIs such that for that set of EIs, this many is needed. Yeah, right, right. Thereby showing that you could not get a general upper bound that was, like, square root of log m or something like that, or that was, yeah, yeah. Yes, that's right. That's right. It is, yes, that's right. It is also a lower bound for full tomography. Right. You can. Yes. Yeah, yeah. So yeah. Yeah, so we talked about this before. You can reduce full tomography to shadow tomography, but only by either taking the list of EIs to be enormous, right, like doubly, like exponential in D size, or by taking epsilon to be really, really small. In either case, the bound you get from shadow tomography on the number of copies of rho will not contradict that D squared lower bound for full tomography. Yeah. Okay. Yeah. Oh. Oh. Huh. Oh, really? That's open? I didn't know that was open. Yeah. Huh. I didn't know that was open. All right. Yep. Yeah. Oh. Okay. Well, that I'm not sure about. Yeah. Not sure. Yeah.
Are there any guarantees as to how close to alpha density your measurements can be on states that are very weakly entangled?
Oh. So we haven't really studied that. It would depend what you meant by weakly entangled, right? So like if I took the GHZ state, right, you could say like in some senses that's only very weakly entangled, right? In the sense that like the amount of entanglement entropy across any cut is very small, right? And and like any the reduced density matrix on any small regions are not entangled at all, right? But the GHZ state is an example that completely breaks our theorem, right? At least with the parameters that we want for the theorem to be non-trivial. But I should mention that I should stress that entanglement is not actually the main issue here. It's really correlation is just as bad. For our theorem, right? Like if I took an equal mixture of the all zero string and the all one string, right? That also breaks our epsilon times square root of n bound, and it forces it up to epsilon times n, right? So so really we should be thinking about very weakly correlated states, but you would have to say what you meant, and okay, like if it's just close in trace distance to something that's a product state, then we might be okay, right? But maybe that's not so interesting. I mean, I think there's it would be interesting to explore further. Are there non-trivial notions of weakly correlated under which our theorem still holds?
Sort of thinking,
Yeah.
You have some qubits.
Yeah.
You think
Yeah.
that they are they're a perfect product, and they're subject to some noise,
Right.
Such that you can no longer write down
Yeah.
the density matrices as a product.
Yeah.
So something, and I don't know exactly how one properly
Or-
formalizes that, but
yeah.
something that would be one might easily.
Or if we had, like, let's say the qubits are in a line and each one is only kind of entangled with its neighbors or something, and the entanglement falls off rapidly with distance. That would be interesting to study. I don't know the answer off the top of my head. Maybe by this afternoon I could give you an answer. Yeah.
So there's a case which we considered when we were looking at, Patrick and I considered when we were looking at matrix inversion
Mm-hmm.
For machine learning.
Yeah.
Now, if your data is in the form of a quantum state,
Yes.
and you have some guarantee that it's, that most of the entries are non-zero,
Uh-huh.
and then you just change one of the entries to something else,
Uh-huh.
then these are very close. The state is now very close to the state in the ordinary method of filter state.
Of trace distance.
Of trace distance,
Yeah.
So
Okay.
I mean, it's not a product state.
Yeah.
It's just a state.
Yeah, yeah.
And then you
Okay.
can use, there are plenty of algorithms that will, where you use things like, quantum matrix inversion,
Hmm.
linear systems algorithm,
Hmm.
that operate on such states.
Mhm, mhm.
And the states themselves have the features that provide that.
Okay. Cool. Yeah, but
Yeah, because I mean, you can show that any algorithm, quantum algorithm, works because the states are, you encode your gigantic vector from your database
Yeah.
to a quantum state, and the quantum states are now very close to each other.
oh, I see. So you're saying this is a way to achieve differential privacy or to achieve
It's a way
some
that
privacy
quantum
guarantee.
things will achieve automatically.
But
achieve
right, but okay,
automatically.
but do you actually learn something interesting about your original data by measuring these states?
Yeah, so I mean, then if you have an algorithm where you're
Yeah.
operating on these states and trying to reveal something about the
Right.
data set,
Yeah.
guarantee that and
Yeah, right. But no, but there's a conditional in what you just said. I'm asking whether there are actual examples where that conditional holds, right? Where you can actually learn something, right? I mean, like if like I had a mapping from databases to states such that all the databases map to some epsilon ball of states, right? Then we would say that any possible algorithm from that point that goes and measures those states, cannot be learning very much, right? Just, because all my states are bundled together in this epsilon ball, right? And then no measurement can then distinguish much. But
you could do principal component analysis, right, on the state, right? To reveal if let's suppose you have a bunch of vectors
yeah,
in your database.
Yeah.
The question is the corresponding matrix, the rows of the matrix. And the question is
Okay.
the corresponding matrix row.
but in some sense, no matter what my database was, right, I can say that I can completely change my database X to another database, Z, and the output by necessity, and if we do what you said, then the output distributions would differ by at most epsilon in total variation distance, right? And so that would like in differential privacy, we typically want algorithms that can give us a much more informative output than that, right? Like, our requirement is if we just change one entry of the database, then our output distribution doesn't change by much. But if we change the entire database, then hell yes, we should be seeing a different output.
So
Right.
I guess maybe
Yeah.
more precisely.
Yeah.
My data in the database is the rows of a bunch of vectors.
Mm-hmm.
And this is a matrix, and the
Mhm.
matrix is all the entries are roughly the same size.
Yep.
So each row, if I were to change it,
Mhm.
if I make it into a quantum mechanical
Mm-hmm.
vector,
Mm-hmm.
if I change one entry, then it's almost the same as one.
That's right.
But then I can use this database
Mhm.
to find out to do singular value decomposition, quantum singular value decomposition, time log,
Okay. Well, I mean, I'm still not seeing how we get around the general argument that I just gave. But maybe we should take that offline. Okay. Yeah.
Okay. So thanks a lot.
Yep.